In this video, we are going to discuss about the Shannon's Hartley theorem. So, on completion of this Shannon's Hartley theorem, students will be able to understand the concepts of the Shannon-Hartley theorem. In Shannon-Hartley theorem, this tells the maximum rate at which the information is transmitted over the communications channel of a specified width. Even in the presence of the noise also, this maximum rate of information can be transmitted over the communication channel for a specific bandwidth. So this it is an application of a noisy channel, and it can be subjected to noise also, and it is an application of noisy channel coding, and this can be transmitted through the channel with the presence of the noise through a specific bandwidth. So this we call it as Shannon's Hartley theorem. This theorem actually establishes the Shannon's channel's capacity, that is maximum amount of error-free communication has the capacity of transferring the information without any error, but it has the specified bandwidth in that it can be some kind of noise noise inference can be present, so that this assumes the signal power to be bounded, which we call it as power spectral density. So this we can written as C is equal to B log 2 into 1 plus S by n, which is equal to B log 10 1 plus S by n divided by log the base power 2. So the graph you can see, considering all the possible multi-level and multi-phase encoding techniques, the Shannon's Hartley theorem states that the channel capacity, meaning that it is lightly tight upper bound on the information rate, and through the analog communication, this channel will subject to additive Gaussian noise. So that is given in this graph, which we called as C is equal to B log to 1 plus S by n, where this C determines the channel capacity in bits per second. And this considering all the possible multi-level and the multi-phase encoding techniques, this states that the channel capacity is having the tight upper bound on the information rate, which does not excludes or includes the error coding techniques. This data which is sent with the signal in a particular bandwidth will contain some kind of noise, which we call it as B log to 1 plus S by n. Here the B is the bandwidth of the channel in hertz, S is the average received signal power over the bandwidth, that is in the case of the modulated signal often denoted as C, that is modulated carrier, which we are measuring in watts or watts squared, and n is the average noise or interference over the bandwidth. So this S by n is the signal to noise ratio or the carrier to noise ratio of the communication signal to the Gaussian noise interference, which is expressed in linear power ratio. And the applications and this uses is, first one, Huffman coding. It is not always optional among all compression methods. Second one is discrete memberless channels. Third one is it can find 100% efficiency using these codings. Thank you.